Assalamu alaikum. Welcome, students. We have comprehensively discussed how we can solve the state equations using MATLAB ODE 45 function in the previous lab sessions. In this lab session, we will model a simple mechanical system using MATLAB Simulink. MATLAB Simulink is a GUI based method for modeling and analyzing a system. In Simulink, fundamental blocks of various physical systems are present. These physical systems can be mechanical, electrical, thermal, biological, etc. etc. Apart from these, there are various mathematical operations present in the form of blocks to be used with these physical systems. We can also create a customized block which may contain our desired equations. I can say any physical system present in the universe can be analyzed using MATLAB scripts and Simulink environment if we can find out the input-output relationship of it. I think that's enough description. Let's start the Simulink environment. In MATLAB taskbar, you will find Simulink written. Here it is. Press this button. It will open the Simulink environment. We can also open the same by writing Simulink in the command window and then executing the instruction. This is called Simulink library browser. You will find various blocks from different fields of engineering. Now let's create the simplest Simulink model. Press Ctrl and it will open a new blank model. Here it is. In this model, I will create a simplest system which will take two numbers and print the summation of these two numbers. So first let's pick up the add block from math operation. Here it is. Right click, add block to a untitled model. You will find in the untitled model the add block here. Now pick up the constant from sources. Right click, add block to untitled. So here is the constant number. Connect this constant number to first operand. Copy this constant, Control C and Control V, and also connect this to the input of the add block. Now change this number. Double click, you will find the window containing the parameters. I am changing it to 2 and I am changing it to 4. So now we have to display the output. So from sync, I am adding this display window to our untitled model. Right click, add block to untitled model, and connect this display to the output of the adder. Now let's simulate this system. Here you will find the play button. So now here you have you can see the result of 2 plus 4 is 6. This model was just a Kickstarter of Simulink environment. Now let's simulate a step response of a simple first order transfer function. I am selecting and deleting this model. Now in continuous section of the library browser, you will find the transfer function block. I am adding it to our model. You can see here it is added. Double click, you will get the window of the parameters of this block. This represents the numerator coefficient. Here it is written 1, so it represents constant number 1. If I write here as 1 space 1, then it will become the s plus 1. So I am again changing it to 1. The denominator polynomial, here it is written s plus 1. I am changing it to s plus 5. Okay. Now you can see the transfer function block is changed to 1 over s plus 5. Previously it was 1 over s plus 1. Now we have to pick up the step input. So in sources, we will get this step block. I am adding it to our model. Connect this step block to the input of transfer function. Double click to change the parameters if required. Here the step time is 1. It means it will change from initial value to final value at 1 second. I am not changing it. Okay. Now we have to observe the response of this system after the application of this step input. So I will be needing a scope here. So let's pick up a scope from the library browser. In the sync section, you will find the scope. Let's add this scope. Now go into the scope by double clicking it. Press this gear button, and in the logging section, make sure you have unchecked this point, limit data points to last. Okay, cross. Now connect this the output of transfer function to the input of scope. Now let's simulate our model. Change it to 5. You can see the step input applied to the system is at 1 second, since the output of the system is 0. The final value of this system is 0.2, which is expected from the transfer function, as the final value is equals to the numerator constant divided by this number 5. So 1 over 5 is 0.2. Now let's simulate the integration of sine wave. As we know, if we integrate sine wave, we will get cosine wave, which is 90-degree shifted version of sine wave. So if I integrate sine wave, I will again get a sine wave with a 90-degree shifted version. So let's do this. I am deleting this model again. From the continuous section of library browser, pick up the integrator here, right click and add this to our model. You can see it has been added. Now pick up the sine wave from sources, as we want to integrate the sine input. Sources, and add this sine block to our model. Now connect the output of sine wave to the input of integration. Now let's check the parameter of the sine wave. The amplitude is 1 and the frequency is 1 radian per second. I am leaving this as it is. Now add scope from the sync section so that we can observe the output of integration. Connect this scope to the output of integration. Now double click, press this gear button and change this number of input ports to 2 and change layout to 2 rows and 1 column. Now you can see here we have the space for 2 plots. Connect this second input to the output of sine wave. I just added this second input so that I can observe the input and output of the integrator. Now let's simulate. This is our input, as it is the second input of the sync, and this is the output of integration, which is the first input of the sync scope. Now you can see this is, plot is the 90-degree shifted version of this plot, but here you can observe that it starts from minus 90 degree instead of 90 degree, as the integration of sine is minus of cosine. Now that's enough introduction to Simulink. Now let's model a mechanical system, which is our actual task in this lab session. So I am deleting this model again. Mechanical system considered for this sake is shown here in the lab manual. Here it is. The mathematical equation for this model will be F is equals to md square x dt square plus b dx over dt plus kx. Now writing state equations from this equation. So the state variables are x1 is equals to x and x2 is equals to dx over dt. So putting these substitutions in equation 1, so equation 1 will become f is equals to m dx2 over dt plus bx2 plus kx1, or x2 dot will be f minus kx1 minus bx2 whole over m. This is the first state equation. Second state equation will be dx1 by dt will be x2, or x1 dot is equals to x2. So this is our second state equation. Now we will use Simulink to solve these state equations instead of MATLAB script. So I am moving towards the Simulink model. In this model, make sure you have selected the type to be fixed in the configuration parameter. Here it is variable. Change it to fixed step and change solver to be ODE8, and in the additional options change the step size to 0.0001 and press OK. Now just see how we write these equations in the Simulink. So first add the integrator from the continuous section in the library browser. Continuous, add integrator in the new model. Here is the integrator. Now assume that the output of this integrator is x2. So the input of this integrator will be dx2 over dt, which is x2 dot. And from the equation b, you can see the, if we integrate x2, if I rearrange this equation, this is dx1 is equals to x2, or x1 is equals to 1 over dx2. So if I integrate x2 with respect to time, then I will get x1. So copy this integrator and paste it. So if I consider the output of first integrator to be x2, then output of this integrator will be x1. Since we have to find out the response of x1 and x2, so I am using scope. So using scope to terminate the output of x1 and x2 both. So output of first this integrator will go to this scope, which is x1. Copy this scope and paste it. Output of the second scope will go to the x2. Now input of this integrator is dx2 over dt, which is x2 dot. So from the equation, from this equation A, we have x2 dot to be equals to this term, which is the summation of three terms. One is f over m, second is kx1 over m, and third is bx2 over m. So I am using adder in the library browser. From math operation, take the adder block. Output of this adder will go to the input of the integrator. Here we have two operands only, and we need the adder for three operands. So I am adding another sign here, plus, minus, minus. You can have this parameter block by double clicking this adder block. So I have written plus, minus, minus, as we have three operands. One is plus f over m, second is minus kx1 over m, and the third is also subtracting, which is dx2 over m. So the first input is f over m, the first operand is f over m. So I am using step input to model it, since it is a constant number. Sources, add step block and make it the first operand, since it is adding. Change it to 0. Step time initial value will be 0, it's fine, and the final value will be f divided by m, as we want the step input to be equals to f over m. Second operand is k over m, so I can write it as k over m multiplied by x1. So I am using gain block present in the math operation to eliminate the k over m factor. In math operation, gain, here it is, gain block. Double click to change the value k over m. Output will go to the adder. and input is the kx1 over m. So the input of this gain block is x1, and x1 from our model is here. Now I am copying this gain again to emulate this factor, which is bx2 over m. So this here the gain will be b over m. Output will go to the add, and the input will we will take input from x2 here. Now we have completed our system here. Now we will simulate our system. Now before going, we have to first initiate the values of f, m, b and k. I have already initialized these values with these numbers. Force is 300, mass is 750, b is 30 and k is 15. So these variables from workspace can also be used in MATLAB script as well as in the MATLAB Simulink model. So let's change the time to 300 and run this model. It will take time. Here is the status. Let's wait here. Now you can observe the plot of x1, which is same as we plotted in lab session 2. The final value is 20, and the x2 plot is the velocity plot, and you can observe that the velocity is 0 after some time, as we observed the plot in lab session 2. We can also export the values of x1 and x2, which is the displacement and velocity respectively, to the workspace by using the toWorkspace block in the Simulink library. It is present in the sync. Here it is, toWorkspace. Let's add this block to our model. Connect this to x1. We have x1, the state variable x1 is the displacement, so I am using x variable here. Change this save format to array, and this save 2D signal as to select this from here, inherit from input, and press OK. Now copy this, Ctrl C and Ctrl V. Also we have to export this variable, which is velocity, so I am using V here. Okay. Now we also have to export the simulation time, so we need another variable, which is t, and the simulation time can be taken from this block here in the sources. So now I am adding this clock to our model lock, and connect this clock to the toWorkspace variable t. Now let's run this model. It will take some time. now the simulation ended. Now observe in the workspace we have x, v and t variables. So let's plot t comma x and grid. So this is the plot of displacement, which is same as we observed in the Simulink. Plot t comma v and grid, and here it is, the velocity plot. So now that was the all about today's lab session. At the end of lab session 5 you will find exercise. I will make Google assignment for it. So that's it. Allah Hafiz.